But first, when we think of military spy drones, most people picture covert intelligence, right? Gathering pictures, gathering video. But what most people don't realize is that these drones are deaf.
That's right. But we met a group of engineers in the Netherlands who not only gave drones ears, they gave them wacky three-dimensional ears that are directional, and that's a total game changer.
Hans Elias de Bray and his colleagues have designed a very special device.
So that one is the nose of the aircraft. Probe comes in, it's the wind cap.
It's called a microflown, a play on microphone.
This is the system we use to get the channels recorded from our sensor.
And they're field testing it for the first time today.
96 kilohertz, 24 bits.
Attached to an unmanned aerial vehicle, Microflown listens for threats in the air and on the ground.
Here you will see the whole autopilot with the wireless link to the ground.
This is the wide-angle camera, looks 170 degrees, all directions. The sound wave is detected here, and then the camera looks at the place where the sound comes from.
The sensors are tiny, less than the head of a matchstick, but their impact is huge.
If you have only sound pressure microphones, you don't know where sound is coming from, only how much sound there is. And with our new sensor you can find out directly where sound comes from.
From a surveillance standpoint, they're completing an otherwise fuzzy picture.
Sound pressure microphone, like your ears, covering only the half of the acoustic spectrum, and we cover the other half. Here's a traditional microphone, which is a pressure microphone, and the three elements you see here are the vector sensors, the microflown sensors, and these give the direction. So the red one does left-right, the blue one forward-backward, and here the green one gives up and down.
Microflones have two heated wires. Based on the air flowing over them, the devices detect noises like explosions.
The first wire will be cooled down, and the second wire will be cooled down less, because the air is heated by the first wire. So what effect happens is the flow causes a temperature difference, and the temperature difference is a measure for the acoustic quantity.
At the same time, they filter out ambient noise.
If the wind comes in like that, it troubles the measurement, and for that we have a wind cap. So under the wind cap is our microflown sensor. Another noise source is the platform noise. That's vibrations which come in from the propeller to the probe, and for that we damp it a little bit. And the third noise is the propeller itself, and the propeller makes harmonic noise. So that noise we cancel with signal processing.
You may be wondering why acoustic sensors are even necessary when we live in a world full of video surveillance.
The problem with video surveillance is that people are not used to looking around. People are used to listen if there's something strange. Then we look in the direction where we hear the sound. We call it classification. So with our ears we classify, with our ears we localize, and our eyes are only used to verify if it's really true what we classified with our ears. So normally with UAVs you have eyes in the sky, and we give them ears in the sky.
Check, 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 check.
He's still programming.
Just putting the flight plan at the right position.
They're like kids in a candy store today.
The man of the serious explosions. It's Major Bomb.
When the UAV takes to the air, they'll set off mock mortar and sniper fire.
He will ignite the explosion, which we will detect.
They launch the UAV and track its progress from the ground.
Now the wind is really picking up, and there's some rain coming in also. So let's see how it performs in horrible weather.
When the UAV hears an explosion, it calculates its altitude and the angle the sound waves are coming from. That helps them pinpoint the source, and then confirm it with video.
Now he's simulating a sniper. When the plane comes in, he makes a shot and we will detect it. Yeah.
It takes time for sound to travel.
If it's, for instance, 300 meters away, it takes 1 second for the sound to reach the sensor, which means the video image is already gone. So what we do now, we video the event, we store the video for, let's say, 10 seconds, and if we detect an event, we move back in time to find out where the picture was, what belongs to the sound. We only send down a picture of what happened. and this reduces enormously the amount of data that's transmitted.
Today's flight proves the UAV can find sniper fire from 300 meters up. Doing it in bad weather makes this team even happier.
It was directly showing what was the disadvantage of cameras. If it rains, the camera doesn't see that much. Finding somebody who shoots, for instance, you only try to find the moment of flash, and it's very difficult. Whereas the noise is very easy. It's a big bang. If you record it, you know directly somebody's shooting, and you can find the direction.
There are obvious military uses for these sensors, but they could be used in aircraft to avoid mid-air collisions, and by police.
Especially for riots, to find out where problems are so that they can act on it.
The Microflown is a groundbreaking device and solves the biggest problem of audio surveillance.
There's a lot of people looking at putting acoustic sensors in the air, but we are the only one who can do that because of our directionality of our sensors. Normally, to get directionality, you need arrays, and arrays are big, and getting big things in the sky is difficult. So there's a lot of effort for acoustic sensing in the air, and we are the only ones that crack it up till now.